What we have been concentrating on in the past years was, let's say, to particular further develop third generation of photovoltaics. So because they allow for diversification, so beyond silicon, and also because the growth rate of this associated technology seems to outperform those of traditional solar cell devices. In that respect, we all have here this annual chart in mind, which we usually like to show at this occasion, just highlighting that the typical growth rates of multi-junction solar cells, mostly silicon-based here, had been in the order of 0.7% per year over quite an extended duration. And single junctions have been working here with, or have been improved with a rate of 0.5% per year in the past years. But it's a particular the sort of third generation or emerging photovoltaics that shows here tremendous growth rate over the last times. And it's this sort of technology that we would like to further push, actually also within the SolarTAP consortium, and to find meaningful and useful applications also for these material devices. The way we would like to discuss this here, also then later in the context of digital twin, is that this defines in particular based on the materials that are considered. So we speak here about perovskite solar cells, organic based semiconductor materials, but also quantum dot solar cells that we try to develop. And this SolarTAP project itself is basically a unification of a larger number of Helmholtz laboratories, so that have an established reputation also when it comes to emerging photovoltaics both through records basically and also scientific publications. And these labs that have been unifying here, so they are located at these three different sites. So Jülich, Helmholtz Zentrum Berlin, and also Karlsruhe Institute of Technology. And it's these labs basically that are mentioned here that have a kind of core technology contribution to what we understand here nowadays as the sort of SolarTAP project. But it's not just about the development of this technology and the further operation of this laboratory infrastructure, but it's also the application of these technologies to new use cases that have been emerging really only in the past few years. And these use cases usually have been defined within the context of so-called dual use or multi-purpose photovoltaics. So in a sense that the actual installation should not just serve the purpose of generating power, but there is also a secondary purpose of this installation associated with this that usually is derived in the context of a particular application. And it's two aspects that are shown here, but in essence, we are working on three aspects. So that is the agro photovoltaics, where we try to install actually PV solar cells here on agricultural grounds in order to improve or to benefit also here from certain aspects that help to increase the harvest actually of agricultural products. Or we also have been working intensively on the integration of photovoltaic devices into buildings. And so where from architectural perspective, it's particularly the color appearance of these cells that is quite appealing and that offers, let's say, new opportunities also in the design of buildings. And this is going to shape a future infrastructure and urban areas actually by integrating these photovoltaic aspects into these sort of buildings. So the starting point actually for most of these aspects is a reputation that these different Helmholtz centers have when it comes to solar cells, of high performance solar cells, using these sort of different materials such as these organic materials, also perovskite solar cells, but in particular in the past years also tandem solar cells that have been attracting quite some attention here in order to have a kind of good energy harvesting abilities. And the sort of whole SolarTAP project, as way it's shown here, has on the one hand these sort of different laboratories located at these three different sites from this Helmholtz Association. But on the other hand, it also has included a large variety of industrial partners within an industrial network that to which we are going to translate actually the research insights that we have been obtaining into practical use cases and also make sure that much of the things that we are developing are really relevant to final products at the end of the day, so that this is not just a research that is driven out of intellectual curiosity, but this is also research that that really helps to foster or to improve basic infrastructure and also devices, final devices. Yeah, and the Solar Tap project basically, as I already mentioned, is structured around these 5 laboratories here, and we are concentrating on the main application areas, so agriculture, building, integration, PV, and the last thing I have not yet mentioned, but is mobility infrastructure. As one can easily appreciate, so as soon as the main purpose is not just of generating energy with these solar cell devices, but there are these sort of secondary aspects coming to a game here. It's of utmost importance, so to mirror also all these experimental developments with dedicated simulation and modeling techniques, so which we have been summarizing here in the sort of digital twin lab, which has been organizing also here this workshop now, where multiple expertise basically comes together in order to work towards digital representations of solar cells in all its aspects. Yeah. And it's this part of the digital twin here, so this part of the Solar Tap project that we are going to look at from now on in more detail. So just to give like a rough introduction, so this digital twin, the idea is that this is a virtual representation of a solar cell in all its aspects. Yeah, so starting, let's say, from material properties, then we are coming here to the optical aspects. So it's the electrical properties that matter, and it's finally also the device aspects that are entirely described here. Leading on the one hand, like to in a forward simulation, like the full prediction of what would be the energy yield of a given installation per year. Yeah. But it's not just this sort of forward simulation that we are striving for. It's in particular also this purpose to make this like a fully differentiable model across all stages of our description, such that inverse design techniques can be used in order to adjust and tweak all degrees of freedoms that are characterizing both the solar cell and also its fabrication process, as such that we can take the best out of a given installation. And that's why all these different aspects here are chained together, that this is really like a holistic type of simulation framework. And in general, we are using then techniques from the broader field of machine learning and also inverse design and optimization in order to work towards this sort of inverse design actually of the solar cell. And with this is also going to extend beyond aspects that people have been looking at so far. And really tries to bring basically the sort of expertise from these different fields together and then to inversely design these kind of solar cells. And this workshop that is going to happen today and tomorrow is structured in such a way that we have a dedicated session, experts speaking about the sort of material simulations, optics simulations, these electrical simulations, and also of these device simulations. And at the end of the day, we have people then speaking about the sort of machine learning framework that is able to stitch this all together and to make this a comprehensive framework for its full description. So just to motivate you also to stay here with us and then to join also these different sessions, we have here an outline of the schedule that we are going to present. So that you can see here. Yeah. So if after this introductory talk, we will start actually with an overview talk from myself, giving an outline in detail a little bit more on what this digital twin is about. And then we have dedicated sessions where we dive into the aspects that are at stake for each of these individual components. So we speak then about materials. We have Olivier Ronson with us. We have these optics simulations where myself are going to speak something. And then I'm very grateful that I've also seen him, Sven Burger, already. Giving a bit more detail on finite element simulations in the context of this optics simulation for solar cell. So this is the day for today, or this is the schedule for today. And tomorrow then we have Thomas Kirchertz and Urs Eberhard speaking first about the electrical simulations. Then we have Seyedamir Orici, also from KIT here, speaking about the energy yield modeling. And last but not least, we have Pascal Friedrich, speaking then tomorrow about the machine learning part and the inverse design at around 3:30. So most of these presentations are in the order of 45 minutes, which gives them enough time, let's say, to balance depth and broadness also a little bit in these presentations. And I can only hope that you can find this useful and beneficial for the overall purpose. So just to advertise also some aspects here. So there are some further events that have been organized by the SolarTAP Consortium, which are shown here on this slide. So there is this Tag der Neugier, yeah, so which is like a public open door day at Forschungszentrum Jülich, where SolarTAP is going to present itself. So we have here on September 29th, we have the International Summit on Organic and Hybrid PV Systems, where SolarTAP is going to present itself also. We have the sort of Solar Industry Day together here with Cleantech organized in Heidelberg. And finally, we are also contributing to this exhibition TechBlick, which basically looks on the future of electronics in Berlin. Yeah, so if you have time, if you're interested in, then we are more than happy to welcome you to one of these events. And for more information, I would like to draw your attention also to this webpage SolarTAP, so that we have for providing information and communicating information. And you're more than welcome also to follow us on LinkedIn, so to stay up to date with the latest developments in the context of this SolarTAP consortium. Yeah. So with this, I just want to ask shortly into the round, is there a particular question from somebody at this point, or shall I just continue with the next presentation? Yeah. So then, Malu,
I have a short comment. Sorry. Just as an information for all of you, we're going to record the workshop today. So if you don't want to be seen on the video, just feel free to turn off the cameras.
Okay, this is I want to say, so I would start. I mean, you record it now, but we can start also particular sessions now. Yeah. So maybe I would stop sharing here. Exactly, if you're not interested in being recorded, then please switch off the camera. Yeah, so then this would help us. Any other questions at this point? Yeah. Okay, so then I start sharing my screen for this overview of the digital twin. And I will also shortly start recording. Okay. Okay, you do the recording, yeah. Okay. Yeah. Okay, let me just okay, so then welcome to this overview of the digital twin within the SolarTAP project. The purpose here of this talk is just to give you like it is 30 minutes, like a bird's eye view on what exactly does this mean, how this digital twin is structured in order to prepare you a little bit also of what are the things that are coming then in these upcoming more dedicated sessions. So the first thing I would like to say is that, of course, there's a larger number of colleagues really that have been involved into the development of the digital twin. So coming from all involved research centers here. So from Jülich in particular, we have people here from Helmholtz Institute Erlangen-Nürnberg, and larger people also here from KIT. So these people are either belonging to theory numeric groups, so that are really active part, let's say, in the development of the digital twin. But we also have a larger number of experimental colleagues involved in these developments here, because this digital twin on its own cannot be developed independent, let's say, from experimental access and from experimental consideration. But we should always strive to think about how exactly this sort of virtual representation of the solar cell can be coupled to what is also experimentally observable in order to make a certain impact here. So as I already said, so this slide we have been seeing already. So this whole purpose basically of digital twin is so that we start actually from a given material, a process, and a device architecture. So we have a kind of consistent computational workflow that couples considerations of individual materials. So basically that tells us how a solar cell is going to look like in terms of its material decomposition. So to the consideration of the optical details, meaning that we need to study how light is going to be absorbed inside this active layer of a given solar cell material. where we're going to generate charge carrier, electron hole carrier pairs, and so a charge generation rate, and where then in the next step, these sort of electronic details basically are described carefully. So how actually an external circuit basically receives then current. Basically, we need to consider also the installation of all these devices, both in location and position and the orientation of a solar cell, for example, you will see is very important. But its final purpose is really to predict like the total amount of energy a certain solar cell is able to provide. So this is what we understand as predicting here the energy yield of the solar cell. And in the best possible world, we'd like to predict this also across the lifetime. So either or also aspects like degradation of the properties of the solar cell are even partially considered, such that possibly a readjustment basically of operational conditions also can be made. And it is an aspect that we have not yet built in, but it's the sort of prediction of this energy yield of a solar cell that we can already do by combining basically all these aspects within a single holistic computational framework. But it's not just the sort of forward simulation that we would like to strive for, because this is something that you might say, or this is people have been doing this for quite some time already. But we want to integrate really all the simulations within a single workflow, and that workflow should be differentiable. And this notion of differentiability is of utmost importance here, and basically means that we can define an objective function. And thanks to this differentiability, we can predict basically the change of this objective function with respect to the change in any of these degree of freedoms that characterize our solar cell. And it's that sort of gradient information then that is very helpful to optimize solar cells and all its aspects from a very comprehensive picture, such that we can really make the best out of a given device that we can possibly fabricate. While this is, let's say, important already when we look just into the sort of energy yield simulation, this gets particularly important if you combine this also with the secondary aspects in the context of this multi-benefit PV, where also the crop harvest basically should be maximized, or the color perception from architectural installation should also be optimized in order to meet certain requirements. And it's particular in these cases, maybe where the intuitive understanding of how a solar cell should look like is going to fade away. And that's why these techniques from this world of machine learning are very helpful in order to identify structures that really serve most optimal in the context of a certain application. And as such, the digital twin basically consists of these 4 different modules, or these 4 different components at the moment that we try to stitch here together. And the first is a description of the morphology of the materials that are going to be grown. The second is the description of the optical properties of these solar cells. So then we have the sort of electrical description of these solar cells, and then we have these sort of energy yield simulations. Yeah, and all these things are brought together into a kind of self-consistent and differentiable form, thanks to these various techniques that we exploit from the world of machine learning and artificial intelligence. Yeah, and at various instances, you can easily imagine this. The sort of outcome from these simulations will also be cross-checked to experimental results, and can be basically compared how well they can predict actually a reality. So what I'm going to do now in the following is to just give you a bit of an overview of what are these methods, let's say, in these different techniques. And then I'm presenting you one example where we apply this digital twin to explore a particular organic type of solar cell. I stress this upfront that so far this is not yet, let's say, a fully digital representation. So to some extent, we also continue to rely actually on experimental data in order to use this sort of digital twin. But at least the sort of initial workflow had been worked out here. And we can use this also in the future for extensions and applications also to very particular use cases and scenarios. Yeah, and in that sense, this is also more of a starting point here, because you will also easily see in the following. So the expertise that you need in each of these individual steps is quite demanding. And bringing this together basically is an endeavor that is going to last for many years actually. But with this sort of initial framework that we have been setting up, so we can have at least a solid starting point also to further extend this. And I might stress this, that the community as a whole is, of course, also invited to make contributions to further refinements and descriptions of this digital twin here. So to start with, just would like to flash some of the ideas that are put in place when we discuss these morphological aspects. So here we mostly rely on phase field simulations, which will be described then by Olivier actually in half an hour or 20 minutes, something like this, how this works. But the idea here is that in this sort of phase field simulations, basically monitor thermodynamic and kinetic properties of the coated solution and processing conditions, which basically predicts then the bulk heterojunctions morphology, and we can have prediction of how exactly the material looks like that is grown under a certain condition. So we cover this with a graph-based analysis of the simulated morphology to derive something that we would like to call here morphology-aware parameters, which are then indicators or descriptors for other aspects that can be used at one point at a later stage in this digital twin, such as properties for how the charge separation basically works, or parameters that describe the recombination and also carrier mobilities in this kind of system. But the primary output here is really that can predict the morphology of the film, and as such we can use then also this morphology in the subsequent optical simulations, so where we describe the optical response of a given solar cell. In this particular case here, this is even a bit special because, as you will later see, the first application of the digital twin had been to organic solar cells. So where we start actually first of all with the prediction of the optical properties of these organic molecules from first principles, for which we rely in our case here on time-dependent density functional theory. So to get like a polarizability of these individual molecules, and then we can also homogenize the material and consider either the amorphous or crystalline domains to come up with a dielectric function that we are going to use to describe the properties of this particular organic thin film. So once you know actually this dielectric function, so of course you can also take them, let's say, from literature data. So it's not necessary to simulate them all from first principles, but this is like one way of making this more self-consistent and not reliable on external tools. But anyhow, we can plug then this sort of dielectric function together with the cell architecture and also the morphology actually that we take from this morphology simulations. We can plug this into Maxwell solvers that solve Maxwell's equations for a given type of solar cell, considering all the spatial details and the material properties. And from that, basically, we can obtain like primary quantities like reflection, transmission, and absorption, but also charge generation rates spatially resolved inside this light absorbing material. So that will be then fueled actually into the next step of this digital twin, where the electrical simulations are going to be done. So in this particular case, these electrical simulations, so they will be discussed in more detail so tomorrow morning or tomorrow afternoon around the same time. And here we mostly rely on drift diffusion simulations, which essentially consist of a set of coupled nonlinear partial differential equation consisting of Poisson equation, continuity, and transport equation in order to predict essentially the IV curves depending on both the temperature and also the intensity, which will be parameters that affect then also the operation of a solar cell in a particular installation, depending on a certain spatial location somewhere in the world. Yeah, and here from these IV characteristics, so that depend then on all relevant parameters, we can go then in this last aspect into the sort of energy yield description, which would be a description of the solar cell at the module level. So where in essence we take meteorological data, so from databases across various locations, and consider also different orientation of the solar cell at which they are installed, with the final purpose then to predict the energy yield basically by tracing the amount of power that was generated every day then across a full year. And it's this sort of energy yield here, so that in essence we would like to predict, and which is like in lowest order approximation the quantity that really matters for us in this description. Yeah. And it's this sort of aspects. So these four different modules that we are going to take together And then after going once through the details of the application of these different elements here to one particular type of solar cell, we show also how to use then this sort of digital twin in order to inversely design a solar cell with respect to a larger number of parameters that are going to characterize this. The structure that we have been applying basically this framework on in the past year is this organic solar cell, where the basic cell architecture can be seen here on this slide, basically consisting of this photoactive material where we have been choosing PM6Y6 as a modern high performance blend, which rather good properties. We have been choosing this also because in general there's a lot of established material and plenty of literature, so from which we can get insight into the properties of how these solar cells is going to look. For specific purposes, which are not so of utmost importance here, we have been looking actually into a semi-transparent application, even so this material itself is not most optimal for this, but this should not harm or this does not affect, let's say, any conclusions from this digital twin. Because anyhow, the idea is that the setting that we are going to consider here is rather exemplarily. This is not meant to be like the only application scenario, but this is merely considered to be one application scenario that we have been assuming here in order to bring these different simulation frameworks in agreement and to describe them together. So just without going too much into details, so these are just like selected examples basically of this simulation results. So we start here with this morphology of this considered material of this PM6Y6, where out of these phase field simulations, we can calculate basically here the volume fraction and also crystalline order parameter for the donor and for the acceptor. From that, basically, we can predict the structural composition of this bulk heterojunction. So whether this is either in a crystalline phase or in a amorphous phase, and whether these donor crystals or acceptor crystals basically have been developing here. At this point, we could have considered such sort of spatial distribution really of these materials directly into the subsequent optical simulations. But for our purposes, we have been simplifying this to some extent, also to keep the system, let's say, a little bit more light when it comes to the first comprehensive representation in this digital twin. And that's why we appreciated that the typical length scales at which we have spatial variation here is sufficiently small with respect to the wavelengths, such that light is not going to see this sort of heterogeneous anisotropic material, but it will rather see an averaged medium that basically averages over all the properties over these length scales. And at these length scales that matter then for us, the material can be rather treated as isotropic, where the dielectric function nevertheless was derived here from the properties of these different materials. Yeah, but with this actually we can do it in the next step actually. So thin film transfer matrix techniques, which is like a very light and easy to use Maxwell solver in order to study the light absorption in the solar cell. The only aspect that is here a bit special also is that for the properties of these materials that have been considered here before, so this PM6 and Y6, we also have been using already computational tools from the field of quantum chemistry in order to predict these properties here from first principles. This is just something I would like to flash. So the idea here is that we do like a structural optimization of these molecules with DFT. And then we calculate the polarizabilities of these molecules using time-dependent density functional theory. And then we use a framework that is called the T-matrix framework for scattering type simulations in order to homogenize these materials and to get a dielectric function that characterizes this PM6Y6 mixture that we can use then for further simulations. So the final result basically from this sort of analysis is shown here. So we see here this polarizability of these individual molecules, PM6Y6. From that, we can, as I said, thanks to homogenization, we can assign also a dielectric permittivity to this full material. Then we can homogenize this material also according to the volume filling fraction that PM6 and Y6 also are going to have. And then we can calculate, or we can predict basically the absorption then of light in these mixtures of these materials. And this is here the computational study, and we can compare this also to what has been measured experimentally. Admittedly, the details are not entirely captured, but particularly the most prominent absorption peaks are well represented. And as such, we have a certain confidence that the properties of the solar cell is also going to be predicted quite reliable. So what we finally do then at the end of this sort of optics section is to predict the absorption rate spatially resolved within the active layer, which is indicated here in this a light red pinkish type of background. Yeah, so and it's this sort of information then actually we provide to the next chain of our simulation workflow, which considers then the electrical details, so that they can use this then for calculating IV characteristics. Yeah. And some of the aspects that I also just show here is that we have this total absorption rate here. This is basically calculated also as a function of polarization and also angle of incidence and all these kind of things. Because for this later prediction of this energy yield, the angular dependent response is going to be important because one has to take care how the light basically hits the solar cell in the course of a day, which is not going to be just normal incidence, but which takes all possible angles of incidence then there into account. Yeah. And then this next aspect is then the sort of drift diffusion simulations that we use in order to predict these IV characteristics of these solar cells. As I said, so this is discussed here depending on the intensity of the light and also on the temperature in order to accommodate these details then here in the energy yield modeling, where the exact placement of the solar cell is certainly also matters. And then we finally go then here to this sort of energy yield. So where we consider at this example here 3 different locations just to show a little bit the applicability of this whole framework. And using this annual data, we basically have been using climate data here from Phoenix, Seattle, and Honolulu, just as representative places for different climates, and to see also what type of implication basically the setting or the environment has in which the solar cell is going to be placed here on its most optimal performance. Yeah. And then the first thing that we can do is to make a kind of forward simulation. Yeah, so we can take basically a solar cell with given properties and details, and we can predict basically the total energy yield. And this is then shown here on the left-hand side at this example of Seattle. I think for the absorber thickness here of 200 nanometers. So then we can change actually the tilt angle, which is in this case, so the angle at which the solar cell is going to be installed. And we can look for the largest possible, or we can look for the energy yield that this given solar cell at this given location for this particular orientation of this tilt is going to provide us. And here we have a certain optimum if we optimize this tilt angle to be 27 degrees actually. Yeah. This is like for one of the locations and for one possible thickness here. And we can also check this, or we can also verify this here for so for different locations. So you see here in this kind of spider diagram, so how the energy yield changes. So depending on the orientation of the solar cell in these 3 different locations. And of course, these angles only vary between 0 and 90 degree. And then we have been adding here one more data point where we also show the optimum actually. So in order to compare what would be the energy yield that we can obtain for a given installation at a certain location for a most optimum angle that you can directly compare here. So we can also have here a few numbers. Where we can compare this then actually also to what had been obtained in literature. And this is then here the performance under standard test conditions, so normal incidence AM 1.5 G spectrum. We can predict then here actually the different parameters, so depending on the cell thickness of the absorber layer. We can compare this actually to what had been experimentally observed. And why there are small disagreements, let's say, in a few last digits. the overall behavior we can predict very well. And considering that this is also like a pure computational prediction, at least we had been quite surprised to see that in a kind of consistent description, we can come so close to what had been experimentally measured. Okay, yeah, maybe we can, okay, yeah. So even going further, so now up to this point, maybe you could say that this is also to a large extent something that people have been doing for quite some time. But our purpose was to work actually towards a fully differentiable version of this digital twin, which means that we want to make an automatic differentiation of this code really at a level of the scientific software. And I guess Pascal Friedrich will speak a little bit more about these aspects, how this is done. So the idea here really is that one writes the software in a suitable way and then basically uses these frameworks such as PyTorch autograd here in order to differentiate the output of this predicted energy yield with respect to all of these input parameters that we are going to see here. Yeah. This is done with techniques that have been developed in the context of artificial neural networks, because there, in general, you have some things very similar. In an artificial neural network, basically, you need to adjust all the weights of this neural network in order to optimize a certain objective function, which is usually done by comparing, let's say, the predictions of the network to labeled data that you have available. And then you use this kind of backward propagation technique, which is very similar to the sort of automatic differentiation at the end here, in order to adjust all the degrees of freedom of this neural network in order to optimize this objective function. And in our case, we are just very close to a kind of physical description of the system. So by really differentiating here with respect to all these physical parameters that are relevant here. And the sort of numerical pipeline basically then is shown maybe here in this slide. So you have this sort of set of design variables, you do your simulations, you predict this objective function. So then you obtain your gradients of this objective function with respect to this design variables. You make an update of this design variables, which is more promising, and then basically you're back in the loop, and then you're going to repeat this all over again. And I stress this, so the key aspect here is how to obtain this gradient information, because this is really the key of the sort of inverse or efficient type of inverse design. Just to say one thing, so of course this could have been done, let's say, with symbolic ways, yeah. So we really think about how to differentiate at a symbolic level all expressions that you have. But this is easy to appreciate that this gets quickly quite complicated. This is extremely memory intensive and also slow. And also symbolic differentiation cannot handle some programming constructs that we usually like to have in all our computer software. Numerical differentiation is also always possible. So meaning that you need to change each of these parameters in a kind of small manner. And then you study the change of this objective function with respect to this modified parameter. But this is computationally extremely tedious, because for n variables, you need to do like n+1 full wave evaluations in order to predict these gradients. And moreover, you're prone to round off and truncation errors, which doesn't make this extremely feasible. And that's why the sort of framework of this automatic differentiation basically came into the game. So where by basically applying chain rules and analytical derivatives for each of these primitives that complex computational workflow basically consists of. So we can differentiate then these objective functions with respect to all degrees of freedom in a quite automatic way. Yeah. So I think this is as much as I would like to say here. But the idea is here really is that you can take your Python code in most of the cases and formulate this Python code in a suitable way to use this autograd framework to perform this automatic differentiation. And the only thing that we have to take care on also as a part of digital twin is that not all our computational tools are indeed already differentiable. And that's why we have to leverage further techniques from the field of machine learning in order to provide elements that permit here a differentiation. And one of the things that was not fully differentiable is this one-dimensional drift diffusion equation, so it is electrical part. But here we basically have been doing it like this, that we have been simulating for a large number of different temperatures, irradiance conditions, layer thicknesses, and all the other parameters that matter to us. We basically have been using a forward solver for calculating this drift diffusion equation, so to predict these key quantities like open circuit voltage and also filling factor. And then we have been using this data here together with this input to train a neural network that is able to provide that sort of structure property relation. And the key aspect now is that this neural network itself has been then differentiable. And then we can use this differentiable instead of this model-driven simulation of this the drift diffusion equation as a part of our digital twin that continues to be then fully differentiable. And this works quite nice. So first of all, we can see here like a verification actually of the prediction of this open circuit voltage, also of this filling factor for a given set of parameters when compared to the actual open circuit voltage and the filling factor that have been simulated here. And this can then be used really as a part of our fully differentiable digital twin. And just to indicate maybe so of what is possible at this point, we see here like in the background, so the energy yield as a function of the tilt angle. So these are just two parameters that are used for illustration here, and the thickness of the light absorbing layer. And then we see that the sort of color-coded scheme has been a full simulation. And these trajectories that we see here are trajectories that were chosen by the sort of inverse design framework. So we really see that depending on the starting condition, basically this inverse design process guides us to a local optimum for this energy yield. And in this case, we have been optimizing in these two parameters. But indeed, this can then be also extended to other parameters that we consider also in our inverse design framework. Yeah, and this is so a little bit the idea so of this full digital twin. So you have a kind of comprehensive chain of simulation tools and modeling tools that you stitch together. You make sure that all of these individual codes are fully differentiable, and then you use basically gradient-based inverse design in order to optimize the solar cell here in all its aspects. And I think this is so far the summary basically of the sort of introductory presentation, which should prepare you a little bit about what is going to be presented in the next individual sessions. And I hope I could convince you that this digital twin is a nice comprehensive representation of a solar cell in silico. So we need to unify really a lot of expertise to cover details across all length scales. And initially we have been applying this here, so organic solar cell. And we have been outlining a path basically to this inverse design using also automatic differentiation. Yeah, and this sort of digital twin, as far as it's presented here, also should really be just a starting point actually for more. Yeah, so on the one hand, we are looking forward to provide this kind of holistic tool to partners, actually both in industry and academia, to exploit these this framework actually for simulation. But also look forward to the community in a broader sense in order to contribute also aspects on how to improve this and how to make the sort of representation more precise and more detailed when it comes really to all aspects that concern this photovoltaic option.